Now, before we move on to the other type of temperature measurement, we have to understand the difference between metals and non-metals. This is a non-metal. And what we have here is we have an atom with a nucleus, and we have electrons happily orbiting the atom. Now, are you all familiar, if you could just give me a smiley face, are you all familiar with this model of an atom? Okay, that's good. So this is a non-metal. The electrons happily orbit the atoms. They're going round, they're good, happy little electrons. They're nice and loyal to their local nucleus. Metals, on the other hand, are different. What makes metals different is that the electrons don't stay loyal to their nucleus. The electrons wander away, and they wander from one atom to the other atom, and they kind of hang around in between the nucleuses in what's called an electron cloud. Now, that is what makes a metal a metal. Because all these electrons are hanging around, because these electrons are totally disloyal, in fact, really what you'd say is these are they're slut electrons. They won't stay loyal, they won't stay at home. They just wander around. Now, because we've got all these little slut electrons running around, then it's very easy to pass electricity. Because if I shove an electron in at one end, what happens is another electron falls out at the other end. So if this was a piece of copper iron, if we got a piece of copper wire, then what we would see is electrons going in at one end and electrons coming out at the other end. And when the electron moves through copper wire, we call it current flow. So metals allow current to flow. Metals do other things, because there's all these free electrons floating around. Metals do other things. They also, the temperature, heat, can be transferred using the electrons. So metals are also good at transferring heat. Another thing that happens is, if any photons of energy happens to come in, all the free electrons are able to assume every possible electron level, every energy level. So light gets reflected from metals. Metals make good mirrors. So that's what's special about metals. They have free electrons. Now, not all metals have got the same number of free electrons. Here I've got two types of metal. In the first case, on the left-hand side, the two types of metal are not touching. They're nearly touching, but they're not touching. The top metal, which I'm going to call copper, the top metal has got loads and loads of free electrons. The bottom metal, which is constantinum, which is a copper alloy, constantinum doesn't have very many free electrons. Now, temperature, if you remember, is the speed at which things move. The hotter you make things, the hotter the atoms move. The hotter you make things, the faster the free electrons move around. When I touch the two metals together, all of the free electrons in the top part have a look over and they see, well, look, there's loads of space in the bottom half. So what they do is, because they're totally disloyal, there's nothing to stop them. They scoot over to here, where there's lots more space. So these loose electrons, they put their little high heel shoes on, they grab their handbags, and they scoot off from the crowded part to the less crowded part. Now, when electrons move from one place to another, they create voltage. So electrons moving from one place to another generate a voltage. This thing, in case you haven't already guessed, this is called a thermocouple. It's a thermocouple. Thermo for temperature, couple for join together. Thermocouple. When you join two pieces of metal together, voltage is created. The hotter you make the junction, the more volts you create. So it's a thermocouple. All we need to do is measure the volts being created and we'll know the temperature. There are tables which we can use to look up the temperature based on the voltage. Now, one slight problem with this, I'm going to draw a voltmeter. Here's my voltmeter. Everything inside the voltmeter is effectively copper. All the wiring in the voltmeter is copper. I'm going to come out, here's the voltmeter lead. I'm going to come out of the voltmeter in copper. I'm going to then have a thermocouple junction to constantanum, and I'm going to come back to the voltmeter in constantanum. So just here I have a junction. Now, can anyone see that I also have another copper constantanum junction? Can anyone see where the other junction is? Yes, well done, Russell. It's at the meter. Here I also have another junction. We call this junction the measurement junction, and we call, oh, I don't know what happened there. We call the other junction the reference. Oh, that went horribly wrong. Reference junction. Now, yes, Eddie, it is, a thermocouple is what we use for measuring the temperature in things like gas cooktops. We also use it for measuring temperature to make sure the flame is there when we have gas boilers, and also on oil rigs to make sure that the flame is there for the flare. So we've got two junctions. Now this leads to a slight problem, because when you look at the wiring of these two junctions, one of them is wired positively, if you like. Here we're going copper constantanum, and that creates voltage. The other junction, and what I've done is I've extended the other junction out, is going constantanum copper. That would also create a voltage. Unfortunately, this one creates a voltage in that direction. This one creates a voltage in that direction. If both junctions are at the same temperature, the two voltages would cancel out and I would measure nothing at the meter. So what we're supposed to do is we're supposed to take the cold junction and stick it in a bath of ice. If you stick it in a bath of ice, then it shouldn't create any volts, so we can ignore it. Now, let's think about this. We're supposed to stick the cold junction in a bath of ice. Now, do you suppose having a bath full of ice is a very practical proposition in a factory or a mine site? No, I don't think so either. So what we have to do, instead of sticking it in a bath of ice, well, what we're going to do is, instead of sticking it in a bath of ice, we're going to compensate for the voltage being created. Now, this is how it works. What I do is I pretend that each junction is, to all intents and purposes, a battery. It's something which creates volts. So, simplifying it, I say it behaves just like a battery. So if you treat each thermocouple junction as a battery, it's easy to do the maths. So, we've got one junction, which is like a battery. And is producing volts in the positive direction. We have another junction, which is the cold junction, which is like a battery, and is producing volts in the negative direction. In order to find out what the temperature at the hot junction is, we need to know the voltage being created at the hot junction. My problem is that the volts being created at the cold junction are going in the opposite direction. So the volts that I end up measuring in my voltmeter are not high enough. What I mean to say by this, let's just say, supposing the hot junction's creating 8 volts, the cold junction is creating 2 volts, how many volts do I see at the meter? Yep, you've got it, 6 volts, because they're in series opposed. So, here's my problem. My meter is giving me 6 volts. What I really need to know, though, is how many is being produced at the hot junction. So what I do is a thing called cold junction compensation. From the equation, from the previous thing, the value that the voltmeter reads is whatever's being produced by the hot junction minus whatever's being produced by the cold junction. What I need to know is what's being produced by the hot junction. Rearranging this equation, I end up with hot junction volts is cold junction volts plus what the voltmeter's reading. So I know what the voltmeter's reading. If I can just work out how many volts are being created at the cold junction, then that will give me how many volts are actually being created at the hot junction, and I will be able to look those up in the table. How did I go? Right, let's go back to here. Okay, so now we're going to run through a couple of examples of how this works, but put simply, if I happen to know that my cold junction is producing 2 volts and my voltmeter is reading 6 volts, then it's pretty obvious that my hot junction is actually producing 8 volts. I go look 8 volts up in the table, and the table tells me what the temperature is. Different types of metal, when joined together, behave differently. Different thermocouples have different effects. Different thermocouples are good for different applications. The basic thermocouples that you'll see used quite often are the J and K thermocouples. They're good all-rounders. T-type thermocouples are good for low temperatures. They're used for air conditioning applications because they're good from like -200 to over 300. So that falls, normal air temperature falls into that sort of thing. If you want to measure very, very high temperatures, anywhere up to 2000 degrees C, you're going to need an R-type thermocouple. The only problem with an R-type thermocouple is it's made of platinum, so it's a very expensive thermocouple to buy. We know what the different thermocouples are by the colours of the insulation. So you identify which type of thermocouple you've got by the colours of the insulation. Now it's important to do this because there are so many different thermocouple standards. And each manufacturer, lots of countries have got their own standard. There's a couple of French standards, 2 international standards, German, a British standard, an American standard, and a Japanese standard. So that if I were to say, okay, what I've got here is I've got a blue outer sheath, so my outer sheath is blue, and my inner sheaths are blue and red. If I had an outer sheath that's blue and an inner sheath, 2 inner sheaths that are blue and red, what type of thermocouple have I got? Yep, what I've got here is an American T-type. Blue and red inner, and blue outer. That's an American T-type. Now, here's what a slight problem that does occur. When the install bloke installs the thermocouples, just as it comes into here's my panel where I'm terminating everything, just as the cables come into the gland at the top, the install bloke strips all the outer insulation away. So now I've got no outer insulation. So supposing I've got a thermocouple, no outer insulation, and it's got now just answering that, is a German J type the same? Let's have a look at German J here. Now, he can't see very well from this diagram, which is a shame, but the difference between them is the polarity. The top one is positive, the bottom one is negative. So you have to look at the polarity also, because that makes a difference. Now let's just suppose, for the sake of argument, I've got no outer sheath, all I've got is blue and red. How many possibilities have I got? If I've only got blue and red, I've already found I've got American T-type. It could be a German J-type. I'd have to check the polarity. Any other possibilities? USA S-type. Let's have a look at that S-type. SSS. Yep, could be one of those. And with that one, you cannot tell the USA S-type from the USA T-type. Any other possibilities? Well, I'm looking at this thinking that does look like red and blue to me. So it could be one of those. So we get to the situation where if the install bloke has stripped away the outer sheath, you're stuffed. What you'd have to do is stick it in a bath of water of known temperature, say a bath of ice water, and see what the resistance is. And then from the tables, you should be able to figure out which one seems to fit. But hopefully you can tell what type of thermocouple you've got, because you have an outer sheath and you also have the inner sheaths. In a practical application where we're wiring our thermocouple back to a PLC, what we do is, to all intents and purposes, the PLC terminal is the cold junction. So we measure the temperature at the PLC terminals, and that gives us the cold junction temperature. Now, what type of temperature sensor shall we use to measure the temperature at the PLC junction? Are you all still out there? Can you just give us a smile if you're actually out there, because I know you can hear me. Okay, I'll give you a hint. PLC manufacturers are cheapskates, so they will use the cheapest temperature sensor they can find. What type of temperature sensor is very, very cheap? A thermistor. So, at the PLC junction, there will be a small, cheap thermistor. Remember, thermistors are accurate to within about 0.1 degrees C. Which means, since we have to know the temperature at the cold junction to compensate for cold junction compensation, what that means is the entire thermocouple system cannot have an accuracy better than 0.1 degrees C. It also means that sooner or later, 3 or 4 years down the line, the thermistor will stop working, because that's what they do. When that thermistor stops working, your cold junction compensation stops working. When your cold junction compensation stops working, all your temperature sensors start reading incorrectly. That's your call out. When you get called and all the temperature sensors have suddenly taken a huge step, it's probably that the thermistor in the back of the PLC has just died the way they do. Now, if we know what the hot junction temperature is, if we know what the hot junction voltage is, we can read that voltage off and get a temperature. And we read it off using thermistor tables, thermocouple tables. And you get a free set of thermocouple tables if you contact a company called TC, which stands for thermocouple. Now, I'll just zoom into one part of the T-type thermocouple tables. The way you read these is by saying, if I've got let's say, if I've got 1 millivolt, there's 1 millivolt. 1 millivolt is generated by 20, and then you go downwards, 6. So 26 degrees C, so it's 6 because we went down, 20 because we went across, 26 degrees C would generate 1 millivolt. So let's just do, I'll just rub that out. Let's just do a quick check. If I've got a thermocouple, or millivolt meter, if I've got a thermocouple and my cold junction, or my reference junction, is sometimes called the cold junction, my cold junction is at 20 22 degrees C. So my cold junction is at 22 degrees C. How many millivolts would be generated at 22 degrees C? .87, says Russell. Let's have a look. Oh, that's not what I want to do. Oh dear, that's not right. Let's grab my highlighter. 22. Yep, 22 degrees C generates 0.870 millivolts. So I'll just draw that onto my diagram. Probably in black. 0.87 millivolts. If my cold junction is generating 0.87 millivolts, if my millivolt meter is reading, let's say, 0.01 millivolts, then to calculate how many millivolts are being generated at the hot junction, I use the equation that I found before, and that's that hot junction equals millivolt, meter, meter. Yeah, let me just rub that out. Meter volts, hot junction volts, equals meter volts plus cold junction volts. So using that equation, how many millivolts are being generated at the hot junction? It's quite an easy one, really. No, not 0.86. Oh yeah, hang on. No, not 0.86. Hot junction volts is the meter volts, which at the moment is 0.01 of a millivolt. Yes, 0.88. So going back to the table, actually not a lot of temperature there really. Maybe I should have chosen a better value. 0.88 is just more than 0.87, but less than 0.91. So it looks like it kind of falls halfway between, kind of falls there. So I would have to say that my hot junction's about 22.5 degrees C. Maybe I should use a better example. 1.0. Let's say, for the sake of argument, that my hot junction is producing 0.12 millivolts. If my millivolt meter is reading 0.12, how many millivolts are being created at the hot junction? 0.99. Yes, 0.99. You are absolutely right. And going back to the table, 0.99. I'm thinking, I'll just use a different highlighter. I'm thinking 0.99 is there. Oops, that's not what I wanted to do. Highlighter. There. 0.99 is there. So I reckon my hot junction's at 25 degrees C. Now, is everybody happy with how we read the tables and how we do cold junction compensation? Okay. Here's another part of the table. Now, first thing, first question to ask, how many volts, just going back to the equation here, how many volts do I see at the voltmeter when both junctions are at the same temperature? You're right. When both junctions are at the same temperature, the voltages exactly cancel out. What sort of a voltage would I see if the hot junction was colder than the cold junction? Yeah. If the hot junction is colder than the cold junction, we actually see a negative voltage at the voltmeter. So although we call it the hot junction, it's not always the hottest junction. The sort of faults we get with thermocouples are the junction tends to fall apart. If the junction starts coming apart, then we don't get a good junction. We get decalibration occurring. If the metal starts to oxidize, we can get decalibration occurring because the metal is effectively changing into a different substance. If the metal starts to change because it's overheated, when you heat metal, you can radically change its characteristics. That's why we heat metal and then we work it. If you're making a sword or something, you heat the metal, you beat it, and then you quench it by sticking it in oil or cold water. And sudden heating or cooling changes the nature of the metal. Shunt impedance can also be a problem. What the shunt impedance is a breakdown in the resistance between the leads. That can cause a problem. Another big problem we have is if we consider the construction of a thermocouple. A thermocouple is, you get generally a probe, and then you have the two metals coming in. You get one metal coming in, forming a joint, and then you get another metal coming in, forming a joint. And generally speaking, the probe is full of that horrible powdery stuff that you get inside MIMS cable. You know the stuff I mean? That white powdery stuff. Now, that should give you a lovely high resistance between the two. But if water, just get that, if water starts getting in there, then now we have two metals, we have voltage, and we have liquid. We start getting galvanic action occurring. It all starts behaving just like a battery, and we're going to start getting false readings. We're also going to start, because water is a conductor, then we're going to start to get differences in our shunt impedances. So they're the sort of things that can give us errors. Water getting into the probe. Now another thing that's interesting, now I'll do is I'll put another sheet up, is if you get your standard thermocouple, there's my one thing, your standard, there's a junction going down, there's another junction. If you get your standard thermocouple and reverse the reaction, so if I put a lot of volts across here, say 300 volts DC across here, then the reaction reverses. A thermocouple creates volts, but when I shove volts into a thermocouple, one end gets hot and the other junction gets cold. It's a bit like an electrical fridge. And that is called the Peltier effect. It's the fact that a thermocouple, the thing that occurs in a thermocouple is reversible. If instead of creating volts we shove volts into it, one bit gets hot, the other bit gets cold. It's not a very practical method of cooling. It uses a lot of power. You don't have to use two metals when you're building thermocouples. You can actually use P and N type silicon. And if you use P and N type silicon, you can make these flat sheets of silicon. They've normally got metal on either side, or ceramic on either side. And when you put high voltage across them, one of the sheets gets hot and one of the sheets gets cold. Now you can buy little fridges in the shops that are little fridges, and you plug them into your car electric heat, your car cigarette lighter, and you can put a beer in them,